Good morning, everybody. Dark matter is a big topic of discussion these days. And I was explaining in my last video how what they mean by dark matter is they've measured stars that are going the wrong speeds according to our theory of gravity, and they think that those stars must be being accelerated by an invisible matter. So wherever they see that they think that the stars are going too fast, and they map in this invisible matter that's supposed to be pulling them faster. Now, flat galactic rotation curves are the reason for the existence of dark matter. The outside stars and galaxies are keeping up with the inside stars, and the whole star arm remains as one piece. But our theory of gravity says that the outer stars should lag behind, and that star arm should never be a star arm in the first place, and how dare it? So there must be dark matter that's holding it all together, and that dark matter must be magically distributed just in the right places. Okay, fine. So that's our invisible matter that our science is proposing to explain why star arms stay as one piece. However, there may be another explanation. And there is, in fact, another explanation, which is that the disk galaxies, symmetrical disk galaxies, can move in such a way that their opposite arms draft each other. And in that way, they lock each other into a complex spin. It's a rose pattern that they use, the 1 to 2 rose pattern. If you rotate a disk once all the way around, but at the same time you precess it at 90 degrees twice, then everything follows each other. It's like everything drafts each other. So that's how galactic arms are staying together, not by dark matter. I'm sorry. And this is proven by asymmetrical GRCs. Now, the flat GRCs that were the reason for Vera Rubin saying that it's because of dark matter, those flat GRCs were the result of them measuring star speeds from the center of the galaxy out to the edge in a straight line. So they measure those stars out to the edge and see how they're varying in speed. And they find that the outer stars are going around just as fast as the inner stars, and that's a flat GRC, a flat galactic rotation curve. Now, of course, they're going to start measuring those GRCs from all directions, right? So what they immediately found was that when they measured the opposite direction from center, they didn't get the same flat GRC. They got a different GRC. It's called an asymmetrical GRC. And they found this for all facing galaxies where they can measure GRCs. They measure from the center to one edge, and they get a GRC. And then they measure from the center oppositely to the other edge, and they get a different GRC. But when they average those two GRCs, the average GRC of those two GRCs is the same as any other average that they take on that galaxy. So if they take a GRC out to the side and then a GRC out to the other side and measure those GRCs and average them, they get that same GRC for the galaxy. So for any one galaxy, they can get its GRC, but they have to take it as the average of any two GRCs that they can get on it, and then they'll get the average GRC. Now, those two GRCs are always different. So why are they different? Well, it's because the galaxy is precessing. That facing galaxy has got one whole side that's coming towards you and the other whole side that's going away from you. So one whole side of the stars appear to be going faster, and the other whole side of the stars appears to be going more slowly. And that's called an asymmetrical GRC. Now, I don't know. They had trouble computer modeling flat GRCs with their dark matter. And they found that they could set it up just perfect, but it would go for maybe one or two rotations and then it would break down. So if they can't computer model flat GRCs with their dark matter, they might have a little trouble computer modeling asymmetrical GRCs with their dark matter. I think it has a lot more to do with how galaxies are moving than any kind of fictitious invisible matter that our present science can dig up. Right? Have a good day.